Okay, so let's look at this problem. We want to find the internal forces at this point C in this simple supported beam with the uniform load. So what I'm going to do to help visualize this is I'm just going to draw a line here at C, and then I'm going to decide whether I work the left side or the right side. All right, so let's look at the load first. Well, the left side and the right side, the loading is the same. So there's no advantage, I think, to that. Also, I have reactions on the left side and reactions on the right side. So this is really no difference, whichever you want to choose. I think I'm going to choose left. It's just smaller. I'll have to draw a smaller free body. That's the only reason. So if I choose left, I'm going to find the reactions at A. So let's do that first. So I'll come over here to the side, and I'll draw a free body diagram, and I will indicate my assumption for the reaction at B and the reaction at A. It is a pin, so there would be a horizontal component possibly. And then I'm also going to replace my distributed load by a concentrated equivalent. So what's the magnitude of that load? It's the area under the curve, which looks like 18 times 3, which I believe is 54. So that's 54 kips. It happens right in the middle. That's 18. So that will be 9 feet and 9 feet. Now remember, I'm going to work the left-hand side, so I want to find the stuff at A. So how do I find my reactions at A? Probably some moments at B. So I'll do that. So let me come here, and let's sum moments at B. Make sure the whole structure is in equilibrium. So summing moments about B, my concentrated equivalent load of 54 creates what kind of moment about B? Positive or negative? Positive. So 54 kips. The moment arm is half the distance, or 9 feet. And then my reaction at AY creates what kind of moment about B? Positive or negative? Negative. And that has a moment arm of 18. So it looks like AY is going to be half of 54. What is that, 27? And then I would need to sum forces in the x direction just to make sure, and of course in this problem AX is 0. So I've got my reactions. So now I'm going to come down here and draw my free body diagram. And on that I'm going to put my reaction forces. I found AY to be 27 kips, so I'll put it on there. That distance is 6 feet. I'm going to replace this part of the distributed load with a concentrated equivalent. So that force will be the area of this part of the curve. Base is 6 feet, height is 3 kips per foot, so that's going to be a force of 18 kips. It'll be in the center of this in the x direction, which is half of 6, so that'll be 3 feet. And then I'm going to come over here and I'm going to indicate that I have, this is my positive shear at C and my positive bending moment at C and my positive axial force at C. I just need to find those values. Now, fortunately for this problem, the order that you do them in is not necessarily important. I can sum forces in the x right now, and you know that AC is 0. I can sum forces in the y, get the shear, sum moments, and get moments. So the order is not that important. But just out of habit, I always like to start by summing moments at the cut first, and making sure this free body is in equilibrium. With right-hand rule as my sign convention, my internal moment is positive or negative? Positive. About C, this 18 kip equivalent force creates positive or negative moment? Positive. So the force is 18 kips, and what's the moment arm? 3 feet. And then I have the moment created by the reaction 27. About point C, what kind of moment is that? Negative. So I'll have a force of 27 kips and a moment arm of 6 feet. So I should be able to solve for the moment at C. It looks like it's going to be positive. I don't know what that is off the top of my head. 27 times 6 minus 18 times 3. 108? Anybody else get 108? Excellent. So 108, and the units are going to be kip feet. And it came out positive. Does that make sense to you? Well, how do you think this structure would bend, deform under that load? It probably turned into a big happy face. So you should expect that you would find positive moment everywhere. By the way, where would negative moment be? I mean, sorry, zero moment. What do you think the moment at the pin is? Zero. What do you think the moment at this roller support is? Zero. That's going to come in handy too later. All right, so let's finish this up by summing forces in the y direction. I'm going to assume up is positive. So I'm looking at my free body diagram. So I've got a force acting down. So that's minus C. I got a force acting down. That's minus 18. I got a force acting up. That's positive 27. So that means the shear at C looks like it's 9. That makes sense?
Dr. Ken,
Yes.
how would that moment be if it was a fixed connection at A?
The moment would be,
Because there is moments of fixed connections, correct?
would it be a fixed connection, and what would be at B?
Let's see, nothing.
So it'd be a cantilever beam.
Right.
It would be a negative moment there.
So there would be a moment.
Well, the previous problem we worked was a cantilever like that, and you remember the moments were negative throughout. Because it has a different, the shape is different. Now, if you made this just a fixed connection and you left this to be a pin, then that would be an indeterminate problem. But I would tell you that the moment would start off probably negative and then go positive, and then back to zero. Possibly. But don't concern yourself right yet with indeterminate structures. You'll have to wait to the spring of 18. It just seems like the distant future, but it's just a year from now. And that's when structural analysis 2 will next be offered, if you just got to have it. And we've already talked about this, so we'll finish it off. I'm going to sum my forces in the x direction, and all I have is the axial force. Yeah.
What was that professor that you mentioned when you were showing us the other side of the observation?
That's my office mate, Dr. Abdel. That's just a different way of doing it. I think that's the way he does it in his class, so you'll have to adjust to that when you get there. All right, any other questions about this? That took a whopping 8 minutes to do. What?